The surface area of pyramids and cones. Like with the prisms and the cylinders, polyhedra need to be broken into all their individual faces, and those areas need to be added together. But the solids that are not polyhedra, such as cones, we do have formulas for them. To calculate the surface area of a pyramid, the solid can be broken into its base and triangles. Okay, so you're going to have some sort of a base here. This appears to be a square. The sides, the lateral sides here, are all going to be triangles versus having rectangles like in the prisms. So if we break it completely into its base and a bunch of triangles, you can figure out the individual areas and then add them all together. But before we can do that, we have to introduce a new measurement, which is called the slant height. The variable that we'll be using for it is going to be L. Okay, the slant height is located here. It's going to be perpendicular to an edge length going up to that top vertex. All right, the reason that you need the slant height is because that is the height of the actual triangle that we've got there. So as we break it apart into its individual parts, you have to have the height of the actual triangle to calculate the area of the triangle. The slant height is different than the true height of the figure, which would be located here, perpendicular to the base. In fact, if I were to connect these 2 points together, we can actually justify that the slant height is not the same as the true height. In this figure, we'd create a right triangle here, which would make the slant height the hypotenuse of the right triangle, and therefore greater than the true height of the pyramid. And you can go ahead and assume that'll probably mean you're going to use some Pythagorean theorem at some point to either figure out a true height or a slant height. For example 1, we're going to find the surface area of the hexagonal pyramid. Okay, it does not say the lateral surface area, which means that we will be including the hexagon that we have on the bottom. And like any polyhedron, what we're going to do is break it into all of its pieces. Okay, so we have a hexagon. We also have 6 triangles. As a side note, this figure does not specifically say that we have a regular hexagonal base. But for the sake of doing the problem, we're going to go ahead and work under that assumption, which would mean that all the triangles are congruent to each other. Okay, so for the hexagon, to calculate its area, that would be 1/2 ASN. That'd be 1/2 times the apothem times the side length times the number of sides. For the triangle, or triangles, it would be 1/2 base times height. Okay, so if we can find all these values, we can just complete the expression and then have our surface area. With respect to the hexagon, the apothem is going to be here, so we've got that number. The side length is this, that'll be 6. The number of sides, of course, is going to be 6. For the triangles, which is going to refer to these triangles over here, the base is going to be the 6. The height, also called the slant height in the figure, is going to be the 9. Okay, so this has actually provided all the values that we need. We just actually need to do the calculations now. And though I could do some mental math, I could multiply these together as 36, divide by 2 to get 18, multiply 18 by 3, and so on. What I'm going to do is just go straight to the calculator now, because what I've done is I've set up an expression that represents the total surface area, and I'm going to go ahead and just let the calculator run those numbers for me. All right, so here it is all filled in. We've got the 1/2, we got 3√3, 6 and 6 plus 6 times 1/2 times 6 times 9. And our answer is 255.5. Units will be inches squared. For the cone, much like a cylinder, we're going to be able to write a formula for the surface area. Here's a picture of a cone with all the measurements that we might be using. We do have a radius, which would be the radius of the base. We do have the true height of the cone, and we also have the slant height of the cone, which would be measured from the edge of the base up to the vertex. And again, that measurement is going to be greater than the true height, and you can easily prove that using Pythagorean theorem. Okay, so here's our cone all together. When we start to break it apart, you are going to get a circular base, which we can easily calculate. So for the surface area, you definitely have pi r squared. In addition to that, you're going to have the lateral surface area, which would be the part that goes around here. What we're going to do is imagine cutting that apart and laying it flat, which would appear to look like this shape here. In addition to that, we're going to break it into a bunch of little sectors, like what we did with the circle area formula. And if we take all those pieces and when we interlock them up and down, we can basically create a rectangle out of them. Okay, so if we can calculate the area of this rectangle, that would be the lateral surface area of the cone. The length of this side here is going to come from the circumference of the base, but it's only going to be half of the circumference because the other half is on the top there. Okay, so that'll be 1/2 2 pi r. Okay, 1/2 the circumference. The height is not going to be the radius of the circle here. It's actually going to be the slant height that we got, so that'll be L. Okay, the 1/2 and the 2 will cancel. Then when we take the product of the length and the width, we get pi r L. For example 2, we're going to find the total surface area of this cone. The formula that we have to work with is this. You've got the base, pi r squared, plus the lateral surface area, pi r L. Okay, and all the numbers that we need are actually in the picture for us. This would be your radius, 15. That would be your slant height, 25. Okay, so the surface area is going to be equal to pi 15 squared plus pi times 15 times 25, which we can take straight to the calculator and evaluate. We've got the pi 15 squared plus pi times 15 times 25, which gives us 1884 well, technically it rounds up to 1885.0 with units of centimeters squared.
Later, blah.